You asked me to elaborate a little bit more on the nature of invertible quantum channels. So the question is, what's so special about invertible quantum channels? Can we understand, or at least have some intuition or some good mental picture about underlying mathematical structure of those channels? What makes them really invertible? Well, let me give it a try. As far as mathematics goes, we have the condition, right? So we know that given a completely positive trace-preserving map E that takes us from B of H to B of H prime, so that is a space of linear operators acting on H to a space of linear operator acting on H prime. So H and H prime are two Hilbert spaces here. We know that such a map is invertible if and only if the following condition here is satisfied. So we go into a Krauss representation and we just look at any set of Krauss operators that specify the map. We know there are infinitely many of those sets, but we just pick up any. And in that set, you just pick up two Krauss operators, any two Krauss operators. And then we require that the product EI dagger, EJ, is proportional to the identity. And the identity here is the identity operator on H. The numbers here, sigma ij, form a density matrix. So it's, mathematically speaking, it is a positive semi-definite and has a trace 1, right? But in fact, we also know that there's a physical meaning to those numbers. So they are really a density matrix associated with the environment. So if you take a Stein spring picture here and include the environment in the evolution, so you have a system interacting with the environment, the two are entangled at the end, and then you just trace over the system, you look at the reduced density operator of the environment, and if you pick up any bases in the environment, so those are the entries in your density matrix. Now, you also know that the choice of bases in the environment determines the set of the Krauss operators. So we have a freedom of choice here, and the two are related. So we can, if we want to just see this condition simplified, what we can do, we can choose bases in the environment where this density matrix is diagonal. So this will give us another set of Krauss operators corresponding to this basis. But this set of Krauss operators is actually very convenient and very easy to work with. It turns out that this set of Krauss operators, each Krauss operator in this set is proportional to isometry. So isometry here, we are talking about Krauss operators, right? So they take us from the Hilbert space H to vectors in the Hilbert space H prime. Now, isometry is a map that preserves inner products. And it's a nice map, so you can always extend it to a unitary operation. So for example, if you want to implement a given isometry here, you can just take your system that lives in the Hilbert space H, just bring another system and to extend the Hilbert space, and then just apply a unitary operator to the two. So that will just generate isometry. Now, the set of isometries that we are dealing with are also mutually orthogonal. So each isometry in the set of the Krauss operator will take the whole Hilbert space H, and without deforming it will just drop it in H prime, but in such way that different isometries will generate mutually orthogonal subspaces. Now, the map itself then is described as a convex sum of those isometric operations. So that means that we just choose one isometry from that set according to some probability distribution pi, and those numbers pi are diagonal elements of this density matrix. So when you diagonalize it, so you have those numbers on the diagonal. So we just choose up just one isometry according to this probability distribution, and we just simply apply it. So that will just lend us, if it is V1, we'll just get a subspace V1, H1, and if it's V2, then we just land somewhere here, and so on and so forth. So that is a very nice and simple map, right? Now, because those subspaces do not overlap, we can see that there's a room for inverting the whole operation here. So as a physicist, you may think this way: okay, well, how about the following quantum operation? If I just perform a measurement, which is defined by partitions into those mutually orthogonal subspaces, so then I can just identify which particular isometry was applied. So I can identify where's my state, right? So this whole Hilbert space ended up here or here or here, and the measurement will tell you where you landed really, and then you can just reverse this operation. You see, when you just restrict the action of V dagger, the Hermitian conjugate of your isometry. So V dagger is not an isometry, but if you restrict it into a particular subspace, so then it's the reverse action is equivalent to a unitary operation. So we can see that there is a room, because they don't overlap. We can reliably just determine the subspace. So therefore, we can reliably determine which particular isometry was applied, and then we can try to reverse it. And indeed, we can do it. And I just you can see that the map that does the job has Krauss operators that are the V daggers of the isometries V. Well, perhaps we can just explicitly show this. So let's apply first E to rho, and then our operator, our map R that we specified here. So this is equal to, in the Krauss representation, we can write the action of those two maps. Well, we just have Pi here, and I will have here Vj dagger Vi rho Vi dagger Vj. Right. So first I'm applying my map E, and then it's just followed by map R. But then we use this property here. So those isometries are special, right? So they are orthogonal. So this pair and this pair here is really the Kroneker's delta Ij identity, and this is a Kroneker's delta Ij identity. So therefore here we have a sum over I, Pi identity, rho identity, which of course then is equal to rho. So you can see that indeed this map inverts this map. So map E is indeed invertible. Now one tiny mathematical thing to check here is this map a completely positive trace preserving map? We obviously we see right away that this one is, but how about the trace preserving property of this one? So we want to reliably invert this operation here. So for this we have to check whether the normalization condition, right? So we want to check the sum of over J, and I take Hermitian conjugate of this Krauss operator, that is Vj, and then I have Vj dagger. This has to be the identity on H prime if it were to be a completely positive trace preserving map. Now it may or may not be. You see that it's not necessarily the case that all those subspaces H1, H2, H3 fill the whole space H prime. So there may be a subspace there that is not populated by the images of H under those isometries here. In this case, we just have to simply do something about it. So first of all, you see that Vi Vj dagger is a projector on the corresponding subspace in H prime. So that's the property of isometry, right? So we have, remember that V dagger V is equal to the identity, but V dagger is corresponding to a projector on the image of V. So in this case, the term V1 dagger projects on H1, so let me call it P1, and then the second term gives me a projections on P2 plus P3 plus so on. So it's not necessarily the case that if we add up all those projectors we have identity. So in order to fix it, we just have to add an extra projector on this subspace which is never really populated by the action of this map. But nonetheless, if you want to define properly the map that goes from the set of operators on H prime to H, you have to fix it. So the best way is just to add any completely positive trace preserving map that takes you from operators on this space to operators on H. So adding this one extra term to fix the fact that you want to have the identity, you just got a completely positive trace preserving map. So so that's how it works. So I think that mathematics apart, I think the most important thing here is to probably have this mental picture in mind. So the reason why we can invert certain quantum channels is because they're a convex sum of isometries, or you can even say a convex sum of unitaries, because each isometry here can be easily implemented in terms of a unitary operator on a larger space. So as long as we can somehow identify which particular isometry was chosen, then we can reverse the action, because we do it, if you wish to think about it this way, we can do it in two steps. First, we are going to identify the image of H and find out which particular isometry was used, and we can do this because those subspaces here do not overlap, they are mutually orthogonal, so there is a good measurement that can distinguish between those subspaces. And once you're there, then you can simply reverse the action of V, because restricted to a given subspace, to this image, this map just is equivalent to a unitary operator, which again can be implemented perhaps just by reversing the way you implemented V in the first place. So as you can see, that there's not so much of a surprise here. Hope it is helpful, and it's certainly going to be helpful, I hope, when we start looking at the conditions that are necessary for the error correcting codes, in which case our H will become the code space, and those subspaces will become the error subspaces, as you will see in a moment.